Okay, so we're going to skip 3.4 for now because we're going to looking at this 3.5 lesson, putting it all together. We're going to actually put lessons 3.1, 3.2, and 3.3 together, as well as reviewing and using the information that we learned in the functions course. So in order to sketch a graph. So to sketch a graph of a polynomial function, this is from the 12 functions course. We're going to, and again, we're going to review and recap all of this. So that'll be a good review of functions. Determine what the x and y intercepts are, what the line or point symmetry is, and we're going to discuss the end behaviors. And then we're going to determine the critical numbers, the intervals of increase or decrease, and classifying those critical numbers, and then determining the intervals of concavity, and if I have any points of inflection, in order to then so we've done all of these before, right? In order to then do a sketch and then state the domain and range. So this would be similar to, let's say, a grade 11, we did that a lot. So just to kind of let you know where these are coming from. All of number 1, which is already listed there, is from the 12 functions course. Determining the critical numbers is from section 3.1. Determining the intervals of increase and decrease is from the same 3.1, but classifying the critical numbers is lesson 3.2. And determining the intervals of concavity and the points of inflection was all number 4 here was all from section 3.3, and then 5 and 6 will be today, this lesson. Now, if you wanted to get those down, I'm just kind of explaining where they're coming from, but I'm going to clear it because what I'm going to do is also add kind of like step 1, step 2, step 2 down here. So I don't want so many numbers in the way. So we're going to have lots of information for us to sketch because again, in functions, we could have sketched just with this number 1. Now we have all this extra information to sketch and determine the domain and range. So let's just jump right into an example. It's only one example because they are very lengthy. And I'm going to try to write, I think there's enough room. Usually I run out of space, and for this one, I just had enough. So probably your regular size of writing is hopefully fine. Analyze all meaning all the 6 points above, the key features of this function, g of x equals x to the power 4 minus 8x cubed. So this is to a degree, a polynomial with degree of 4. So after I have all the information, then obviously sketch it and tell me what the domain and range are. So like I said here, let's just color code to get the, to get the intercepts here. Number 1. Oh yeah, I'm gonna need to, the thing is I'm gonna run out of room, right? Just in terms of the numbers up here, that's all. So I'll leave it up when I can, but sorry, I'm gonna have to move it eventually and erase what I have. So just keep up with me. So number 1, let's start with the x-intercept. So this could have been from what, back in grade 9, x-intercept, let y equal 0 of our original function. So if our original function here, this is where y would be. Just put 0 in its place, x to the power of 4 minus 8x cubed. And then in order to solve for x, I'm going to factor, which is what we've done all throughout. So I have an x cubed that's common, which would leave me with x subtract 8. So therefore my x values would be x cubed equals 0, so therefore x would equal 0, and 8 minus 8 would equal 0. So my x-intercepts, so just here, therefore, my x-intercepts, I just do it like this for short, are 0 and 8, but I can make those as coordinate points, right? Because I already made y equal to 0, right? Let y equal to 0. So if one of the x-intercepts is 0, the y value is 0. And if the other x-intercept is 8, then I know that y is 0. So there's 2 points I already have to put on my graph, right? 0, 0, and 8, 0, but intercepts, right? I need to also get the y-intercept. So again, to get the y-intercept, I'm going to let x equal 0. So in this case here in grade 9, I wouldn't have used g of x, so I'm just going to write it out as y and just put 0 in place of x, right? So 0 to the power of 4 minus 8 times 0 cubed. Well, that's 0. That's 0 times 8 is 0. I'm going to end up with 0. So when x equals 0, y equals 0. So therefore, I have a y-intercept of 0, 0, which that point already exists, right? So that's just kind of confirming it, right? If I had, I don't know, a different value in here that didn't line up with that, then maybe I've done some math wrong there. So 0, 0, and 8, 0. So that didn't help me with an additional point, but that's okay. So then for number 2, symmetry, let's change the color here. So to do number 2, symmetry, like I said, I have a polynomial with a degree of 4. So it's an even degree function. Just to write that down, we have right now an even degree. I'm just going to go short form here. We have an even degree function. Excuse me. I don't have any water with me, so hopefully I don't have to pause and go get something to drink if I'm coughing. And it could have, right, line symmetry about the y-axis or elsewhere. Because it's an even degree, it does not have point symmetry about the origin or elsewhere, right? So we wouldn't have that if it's an even degree, but we could have line symmetry. So what we want to do is we want to look at our original function. So it's right there, so I'm not going to rewrite it out again. G of x equals x to the power of 4 minus 8x cubed. And here it's just kind of, it's guessing. So I want to choose a value to sub in for x. It's supposed to be an e there. Choose a value that will not, so I don't get a result of 0. Choose a value to not result in a 0. So 1 sometimes can, 1 can be a little bit, so I'm just kind of thinking ahead, right? So if I was to pick a value of 2, and if I was to plug 2 in here, would I get a value of 0? And if I think I probably wouldn't, then you might want to go ahead and plug in the value of 2 and get an actual number. So 2 to the exponent of 4 minus 8 times 2 cubed. So 2 to the exponent of 4 is 16. And then we've got 8 times 8 minus 64, which would then give me a negative, right? So negative 48. So there we go. I don't have 0, so that's good. It's not 0, so that's good. And then I want to pick the opposite value of that, right? So if I had put in a value of 2, what's the opposite number to 2 is negative 2. So if I plug in a value of negative 2, then I have still negative 2 to the power of 4. Even number would be 16. But now I have negative 8 times negative 8, negative 2 cubed. So I have 16 plus 64 now. So it will be a different number, positive. And I have a value of 80. So are they the same? Are these values the same? Is what you want to look at. No, they're not the same. So that means I don't have any line symmetry about the y-axis. And we'll come back and revisit that when we graph it and make sure that it's not there. So therefore, no line symmetry along the y-axis. If I were, just before I move into the end behaviors here, if it was an odd degree, so we talked about this is an even degree function, right? If I had an odd degree leading coefficient, odd degree function, I'd be looking for opposite results. If the results here were opposite to each other, if the results were opposite, then I would have point symmetry above the origin. So in order to get again, it's not written there, but point symmetry as opposed to line symmetry. I'm looking for opposite results here. Okay. So now let's talk about the end behaviors. What colors have I used? Dark blue end behaviors. Step 3 here, I can fit that in. I can probably fit everything part of the next step, part of this number 2, but then when I get to the chart, I'm gonna have to move it. So end behavior, just to categorize everything here. So again, if you number these off for me, and we just make it so it's easy to follow with these questions that are so long, right? How am I supposed to follow what you're doing unless you organize yourself in some way? So again, we said g of x is a degree of 4, which is even. So if I have an even degree function, my end behaviors will be the same. So maybe we just write that out for review. Even degree function. Sorry, I'm just going to write it underneath here. My end behaviors will be the same. And if it was odd degree, just to save on space, I'll keep going here. And if it was an odd degree, then my end behaviors would be opposite. My end behaviors, I'll go way out here. Would be the opposite of each other. So one was up and one is down, or one starts down and the other end value would be up. So what I have to do is look at my leading coefficient. So with the highest exponent, so my highest exponent is 4, my leading coefficient would be 1, but it's also, is it positive or negative, right? So my leading coefficient, just to summarize, there is 1, but really what I'm looking at is that it's positive. Okay, so because it's positive, both ends will be up. The right end is up, and well, actually, because it's positive, just the right end is up. Let's write that down first. The right side, so reading a graph from left to right, the right side would end in the upward position. But because it's a value of 4, right? Because it's a 4 degree, that's why both ends are up. So even degree function and behaviors are the same, right? So if it's an even degree function and both end behaviors are the same, and we know that the right end is up, then therefore both ends are up. That helps us with how the graph is going to start and how it's going to end. So both ends are up because it's an even degree function. So I'll just say like because it was a degree of 4, but because it's an even degree function, right? So that's a quick recap from the functions course, from the 12 functions course. So now we're going to start here with what we've done in 3.1. Excuse me. So let's determine our critical numbers. I can start some of it here, I guess, without having to move it yet. So this will be step 4. Step 4, finding our critical numbers, step 4. So again, our critical numbers have to do with the first derivative, right? So we have our original function there. I don't think I need to rewrite it. So the derivative of that would be 4x cubed minus 8, 16, 24x squared, right? 4x cubed minus 24x squared in order to get what the critical numbers are, the x values I want to factor for x, which just means set it equal to 0, my first derivative equal to 0. 4 is common and x squared is common here. So I'm going to be left with just an x And 6, 12, 18, 24, I get a 6, and that's it because the x squared was pulled out. So I have 4x squared multiplied by x minus 6. So therefore, 4x squared equaling 0. I have x equaling 0, and I also have x equaling 6. So therefore, the critical numbers are x equals 0. Remember in numerical order, and 6. So sorry, I'm going to have to erase this, but we're going to be obviously continuing with number 4. But basically what we're figuring out now is the intervals of increase and decrease. So technically I'm going into number 3 here, the intervals of increase and decrease. So we're going to make that step 5 anyways. So hopefully you can see the purple. Intervals of increase and decrease, we're going to look at number 5. And number 5 is doing our first derivative chart. So just remember, I'll carry that forward that our critical numbers are 0 and 6. Let's move this up a little bit now. There. So number 5. And if you look on the handout too, on the back, on the second page, you just have the graph down at the bottom. You have all the top of that is also finishing off this question. I have basically the rest of 5 here on the first page just to help you out. And then for 6, when I'm getting my number 4 here, my possible points of inflection, all of that fits on the back. So in order to make my chart, I need to, so again, my critical numbers were 0 and 6, but also when I do my number line here, I'm going to be indicating that my critical numbers are 0 and 6 too, right? So I don't really have to copy that down. I have that in here, and then I'd state that this is the x-axis. This is positive infinity. I can't really fit it in there, but that's negative infinity. So I can determine that I have 1, 2, 3 intervals here, right, to worry about. So if I have 3 intervals, I'm going to have 4 columns in my chart. So the first part of my chart is the factors of the derivative. So I'll do my chart over here. There should be room. Factors of g, it's g prime of x, the derivative. And then my intervals. So I have my first interval between negative infinity and 0. My second interval was between 0 and 6. And my third interval is between 6 and infinity. Just now I have to list my factors, which, sorry, that's erased from here, but that was just in the step down here where that I labeled number 4. I had 0, and then when I factored, 0 equaled 4x squared. I can put it over here. 0 equaled 4x squared, x minus 6. So then my factors of the derivative, right, because this is the derivative, would be 4x squared, x minus 6, and then I have the overall sign of g prime of x. I'll just fit that in there so I don't go overall sign by multiplying them. And then that's going to tell me this is the first derivative, right? This doesn't talk about concavity. This is talking about if I'm increasing or decreasing in reference to g of x. I can say that, I guess. In reference to the original function. So now for my answers, again, you can pick anything between 0 and negative infinity for the chart. So again, you can pick -2 if you want, just to make sure you're getting the same thing as me. -1 squared is positive, times by 4 would be positive. -1 minus 6 is staying negative, right? If you owe someone $1, you owe that same person or someone else $6, you now still owe money. Multiplying these two would give me a negative. So this would be decreasing in the original function. You can fit decreasing, just a D is fine, whatever you want to write. A number between 0 and 6, but I can't choose 0, remember, and I can't choose 6. So 1, 2, 3, whatever you want. This would be positive. 1 subtract 6 is still negative. So I have a positive, subtract a negative, same as here, I have a negative. So this is still decreasing. So again, don't make that assumption that it's going to be every other one all the time. Decrease, increase, decrease. You have to actually do the work through the chart to get the answer, right? You never know what's going to show up here. And then I can't choose 6, so I could choose 7, 8, 9, 10 if you wanted. 7 squared would be 49 times 4. I just care that it's going to be positive. 7 take away 6, be careful, would be positive this time. So multiplying those together would be positive, and I would have an increase at x greater than 6 along in the original function. So just to do my summary here, if it's decreasing and then it continues to decrease, then I don't have anything changing there. But if from here I was decreasing and then I'm increasing, right? Then along this point, I have a local minimum. That's the lowest point. And I have a local minimum at, where am I? X equals 6, right? So therefore, I'll put my therefore over here on the right-hand side because I'm going to go to the next page after this. So therefore, my original function, right, which is what I'm looking for, g of x is, you could have said decreasing first, it doesn't matter. G of x is increasing when, take a look at the chart, increasing only beyond 6. So I could write that as g of x is increasing when x is greater than 6, but not equal to, because I'm not able to choose that number, right? So comma and g of x is decreasing now there's two intervals here where it's decreasing, right? So g of x is decreasing when I'm between 0 and 6. So you could have 0 between, and then 0, x is greater than 0, x is less than 6, but it's also beyond 0 all the way to negative infinity. So really it's just when x is less than 6, right? It would cover everything. Even though there's 2, I can just write it once to cover everything. So if I want to figure out what my actual points are, so I have a local minimum, but what is the y value of that point, right? So let's just write here, I have a local min. I have to sub in that x value of 6, remember, into the original. So I have a local min g at 6 equaling 6 to the power of 4 and minus 8 times 6 cubed. I didn't write, just write down the final answer for that. So if you were to take 6 to the power of 4, then 6 cubed, right, bed mass times negative 8, subtract those, you should have negative 432. Just double check that. So therefore I have a minimum point, a local min at x is 6 and negative 432. So this is just something to consider. We're going to be graphing this. That's a very negative number for y, right? So just when I'm graphing, I have to make sure along the y-axis I'm using a scale that will get me down to negative 432. So I'm just checking the back. Yep, that is everything for number 5. And again, number 5 was figuring out the intervals of increase and decrease there and classifying the critical numbers. So now we're in number 6 here, just to point out here before I flip it. I don't really remember. I don't think I chose brown. So let's do number 6 here. It's talking about the last lesson, the intervals of concavity, and then the points of inflection. And again, here we're looking at our second derivative. And for intervals of increase and decrease, we were only working with the first derivative and doing a first derivative chart test. And here we're doing a second derivative test. And then the sketch won't take us too long to do in domain and range. Okay, so this is the part I'm doing number 4 here. I'm just going to move this onto the other page. So number 6, possible points of inflection. Because again, we don't know for sure until we do the chart if there are any. So possible points of inflection. So again, we just wrote there that we have to do the second derivative. So I don't have the equation in front of me, so I should rewrite what the original function is. G of x equals x to the power of 4 minus 8x cubed. And in order to get the second derivative, why don't I just copy down what I had for the first derivative? 4x cubed minus 24x squared. And then what I need for this question is g double prime. The second derivative would be then the derivative of the first derivative, 12x squared, double 24 minus 48. Don't forget the x is still there. And then what I want to do is make that equal to 0, make the second derivative equal to 0, and then we're going to test around those x values, right? So set that equal to 0. 12x squared minus 48x. So again, if 12 times what squared would give me 0. Oh, sorry, I have to factor first. So factoring first, we've got a common 12 and a common x. So if I take out 12x, I'm left with x minus what gives me 48? 4. Now I can say that my x is equal to 0. 12 times what gives me 0. And this would be a value of what? Minus 4 to give me 0. Right? So therefore, just to say what information this is giving us, you can write this just underneath here, just for me in case for space. I'm going to put it over here. They're still possible. We haven't done a chart yet. So because we haven't done a chart, we still don't know for sure. But these are possible points of inflection. Possible points of inflection are at x equals 0 and 4. So to determine concavity, I'm now going to set up a chart. To determine concavity, right? So again, here I'm going to make my number line. My number line only has 0 and 4 plus the infinities. Positive infinity, yes, this is an x-axis, negative infinity, to tell me that I would have 1, 2, 3 intervals that I'm working with. So because I have 3 intervals, I know I'm going to have 4 columns. That just helps me set it up. So my first let's say column is factors of the second derivative, g double prime of x. Make sure you put g double prime of x. And then my intervals. So I have an interval from negative infinity to 0, 0 to 4, and then 4 to infinity. And create my chart. Hopefully you don't mind doing these charts because we've been doing a lot of them lately. So my factors of g double prime are right here, right? 12x, only 2 and x minus 4. And then I have my overall result looking at multiplying the factors of the second derivative. And that's going to tell me my concavity. So again, this is not increasing or decreasing. This is going to tell me if I'm concave up or down. along the original function. So it helps to write that along the g of x function. All right, let's pick some numbers. Again, whatever you want. -2, I'm going to pick -1. So that would be negative. -1 minus 4, negative. Multiplying those together, though, is a positive. So negative, negative, positive. I'm looking at this value here to tell me that I would be concave up in this case. 1, let's say, that would be positive. 1 minus 4 would be negative. So now I have a positive multiplied by a negative is negative, and I'm concave down here. Let's pick a value of 5. That would be positive. 5 minus 4 is still positive. So multiplying those is positive, and again, I'm concave back up. So I'm going up, down, and up. So again, this is where I'm looking at this overall row. This is where I'm looking to tell me if I have any points of inflection. So because remember the signs have to change. So because the signs changed in the overall row, there are points of inflection. So I'm just going to, just to not write it out the long way, points of inflection. Changing from positive to a negative sign, I have a point of inflection here at what? X equals 0. And then I have, again, changing, sign is changing from negative to positive, means right along here, I have a point of inflection at X equals 4. So I do have 2 points of inflection. So I can put a therefore statement here. Therefore, the original function, right, along the original function, so g of x is concave up when g of x is concave up when I am less than 0 and when I am greater than 4, right? So when x is less than 0 and when x is greater than 4, if these inequalities don't work for you, you know, you can write it out the other way, right? X belonging to this interval, bracket this interval, and x belonging to this interval here. And g of x is concave down when, take a look at the chart, g of x is concave down just in between, within that interval. So when x is between 0 and 4, not including those numbers, right? So there I have my, my x values of, and I know that there are points of inflection where the curve will twist and change from concave up to down, and then twist and curve and change from concave down back to concave up. This is the smile, right? Down is a frown. So upside down is concave down, but I need to get my coordinates, right? The y values. So just to write out here, I'm just using a random different color. So to determine the coordinates, where do I sub it in? To determine the coordinates, try to remember. Anytime I'm subbing anything in, I'm subbing it into the original, right? So I'm using these x values of my points of inflection. So I'm going to sub in g at 0. Again, here, my original, so 0 to the power of 4 minus 8 times 0 cubed. I guess, sure, for the first time, I'll write it down. Minus 8 times 0 cubed. It's just going to be 0, right? So when my x value is 0, my y value is 0. I already have that point existing on the graph from what was at number 1. My, I believe it was an x and a y intercept, I believe, right? But this is also telling us that it's an inflection, a point of inflection. So I know that there's a change happening there. And now at g at an x value of 4, I have 4 to the power of 4 minus 8 times 4 cubed. Again, you guys do the math. And you should get negative 64. So again, I have a point of inflection. There's a change happening at 4 X value of 4 and negative 64. The concavity is changing. So I'm pretty much ready to graph now. I should probably, because I have a bunch of information on like page 1, and I have a bunch of information on page 2 or the front side of the page, if hopefully you printed it double-sided. Let's just write out all the information I have right beside the graph. So I know what I'm doing here. So I am going to get rid of this. Okay, but we will summarize and put it all here. I'm just going to switch back to black. Yeah, I'll do my graph in a different color. So to start, my x-intercepts, right? My x-intercepts were 0, 0, if you remember, and 8, 0. Y-intercept, I mean, yes, it is already common. It's the same as the x-intercept, but just to know, whatever, it's only going to be 1 point. But my y-intercept is 0, 0. I'm starting out, both of my end points are ends up. So I'm just going to write 2 ends up because it was degree of 4, and my my initial number on the highest power on the x to the power of 4 was a 1, so it was positive. So if it's positive, and I know that because it's degree of 4, it's the same, then they're both going in the same direction. So 2 ends up. I had I'm just looking at the front side of the page, a local minimum at, remember that big number, 6 and negative 432. So I have a local minimum at 6 and negative 432. So again, a minimum would mean that it would be concave up, smiling. And I have a point of inflection. You could put POI, I just don't. I mean, we're not talking about any points of intersection here. So hopefully you know that it's point of inflection. At what we just did was 4 and negative 64. I also have one at 0, 0. I guess I could include that as well, right? I should. So I think I'm ready to go. I think that's everything. So I need to be careful here when I'm graphing. So my x values, my highest x is an 8. So in terms of this, if I was to go in the middle, I might not be able to fit to positive 8, and I don't need any negative numbers along x. So I might as well move the y-axis over to allow me more room for the x-axis. So I'm just going to do it, let's say here. Hopefully you guys will see that there. I know it's not 100, well, it's pretty close. Like I'm supposed to be on the line, right? Y-axis, and then same for my x-axis. I have to get all the way down to negative, if I look at my x's all the way down, remember to, sorry, my y-axis. To know where to put my x-axis, I need to look at my y numbers, and I've got negative 432. I also have negative 64, but this is the largest y value, and it's negative. So I need to make sure I can fit. So if I just go, let's say right here along my x-axis, so what I'm doing is pushing it up, then I have a lot more room along my negative axis there. Now I need to determine my scale. So to fit to 8, hopefully we should have enough room to go by 1s. So write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The last one is 11, which matches my notes. Just make sure. Sometimes when it's a small graph, like in front of you, I find, but when I'm doing it here online, you can tend to get these mixed up, and just double check that you've got your numbers correct there. And along the y-axis, if I need to get to negative 432, so let's say negative 450, if I went by 50s and just double check, so that'd be negative 50, this would be negative 100, 150, negative 200, negative 300. There's my negative 400, there's my 450. I've got room. little bit extra, negative 500 technically fit to negative 550. And then this would be 50, and I'm just writing every other one. So that would be positive 100 there. So I've got my scale. The easiest ones would be to label my, let's say, x-intercepts, and sure, we'll say y-intercepts is red as well. So 0, 0, and 8 and 0. And my 2 ends up, I'm going to worry about after. I'm going to skip that and just plot all my points for now, right? I have a local minimum. So again, I know that from that point, I'm going to be going up on either side because it's going to be concave up. Let's plot 6 and negative 432. I think green, hopefully you guys can see. 6 and negative, there's 400, there's 450. I don't want 450, so I want to go somewhere 2/3 of the way down, let's say. Right there. And then my points of inflection are at 0, 0. So I know that that's going to be a spot where I'm changing from concave up, concave down, or concave down to concave up. And at 4, negative 64. So that's negative 50, that's negative 100. So again, halfway is negative 75, technically just a little bit above that. So like 1/3 of the way down or so. Okay, I'm just trying to make it big enough so you can see it once I draw, including when I draw on it. So there's my 4 points. I have to figure out, okay, like how is this graph? So now I can go back to my 2 ends up. So now I'm starting my end behaviors here up, right? And I'm going to end up. And then from the red dot to the blue dot, well, let's start here where the green one is. I'm going to graph it, I guess, in what? Brown. Remember we said that this point here is a local min. So if it's a minimum, I know I'm coming up from that point and up from that point. That's going to be my lowest point. Sorry, I know I'm covering the green dot. So if I'm coming up, right, and if my ends are up and I'm starting up here and coming down, it's supposed to be curved, doing the best I can, and then here coming up. And you can put arrows on the graph indicating that it's going to continue. And then at the point for negative 64, it's a point of inflection. So at this point, it's a point of inflection. So if from the green to the blue dot here, I know that this is concave up. So I know that I'm going like this. And I'm going to do the best I can here. Like this. Yeah, let's try that again. Maybe if I have a bit of a thicker line. Let's pick. How do I pick a different thickness? Let's try that. Okay. So if I'm going there, that helped. And I know that this is a point of inflection. So I know here I was going concave up. Then I know that from this section here, if that's an inflection point, right? And this is also concave up, that now I'm going concave down. So I need it to look somewhat like this right here. And you're just doing the best you can. Use pencil, and then, so that should look like a twist, like an inflection, point of inflection there. And if my, and see here also point of inflection 0, 0. I'm going from concave down, twisting and switching to concave up. And then again here, if I was, that's a minimum point, then I'm coming up. Perfect. And then my ends are up, so I'm ending up. So you've got a couple different places for most of them that you can use like 2 pieces of information just to kind of validate and double check that you're doing that section of the graph correctly. And anything further to write down just to kind of conclude? Well, we haven't done our domain and range yet. So again, yeah, before 0, just to write this down because it was still relatively new lesson from last time. So before 0, I was concave up. Before 0 on the x-axis, I was concave up. So that would look up, smile, happy face, like that. And then between 0 and 4, between x equals 0 and x equals 4, I'm just going to assume the x there. I'm concave down, and this is from the chart, just up above as well, right? And concave down is a frown. So there's my down part. And then I'm concave up for the rest of it. And then my other endpoint has to be ending up as well. So for my domain and range, domain, remember this, we did this a lot in grade 11. X belongs to the set of real numbers because it's a continuous curve there. X is going to continue to the left, continue to the right. There's no restrictions on that, right? My range, is that the same thing happening? Y is my range belonging to the set of real numbers. I'm going to continue on to the positive Y, but I do stop here and don't go any lower. So I do need to such that in there, such that Y is, what value is that? Negative 432, right? So Y is greater than, it is or equal to negative 432. Greater than, because it is a solid closed in circle there, right? 432. And if you just take a look, we already determined that I don't have any line symmetry about the y-axis. We did that in number 2, step 2 that we did. But this just proves it here, right? Along the y-axis here, I don't have any, you see I don't have any line, it's not symmetrical. I don't have any line symmetry, but we can just write that down just to go over that. No line symmetry about the y-axis we're looking at there. All right, so there's our graph.